Hi all, welcome back. So let's get started. This is October 15th, 2020. It is a Thursday, so happy Thursday. Let's make sure that we are staying on track. The market period is almost over. The market period ends on October 23rd. However, we will give you until October 25th to hand in materials as well. But make sure if you owe a lot of work, do not think that we're just gonna allow you to hand things in and not have a discussion with us. We are communicative beings, so we will communicate. So be prepared. Mr. Schwartz and myself will be hosting tutoring sessions after school on Zoom, starting from 2:15 to about 3:15, and basically you must come to those sessions if you want the homeworks reopened or the quizzes reopened, because we need to have a discussion on what is expected from you in the future and how we can make sure that you are not stuck in this pattern again when market period 2 starts. Remember, we're all just trying to be better people than we were yesterday. So let's go ahead and get started. You do have a quiz. Make sure you take it. It opens up at 8 a.m. It closes at 4 p.m. Um, do not take it. We will not give you class time to take it. Reason why? You have an hour and there's no pausing. So we want you to use the full hour if you need it, right? Completely. So you don't want it interrupting any classes. So you can take it, obviously, in this morning, or you can take it after school. You'll have plenty of time. Obviously, if there's something comes up and you have a lunch break right after the class or before a class, you can take it then. We're not judging you. We're not telling you what to do. Just letting you know that you have a quiz, you have an hour, and there's no pausing. The quiz will be on Test Wizard. All right. So today, our learning target is I can use kinetic molecular theory and Avogadro's law to solve gas law problems. Now, we will not be solving gas law problems today. We are setting ourselves up to solve gas law problems tomorrow. Like I said yesterday, this is literally our last section, and we are done. So tomorrow we'll learn about gas law problems, and once you understand gas law problems, I believe doing every other problem that you realize is gas law becomes so much easier, right? So let's go ahead and learn about kinetic molecular theory and Avogadro's law. So there is a text reading. Go ahead, take the next 4 to 7 minutes, read the text. I know it's a little bit hard to annotate because the text is a picture. However, as you know, pay attention to vocabulary and important information. If you need to write it down in the margins, you can make comments in the different sections, and you can then later on use this. So go ahead, use your 4 to 7 minutes, and be prepared to answer those text-related questions. Pause me now and take your time. So we're back. So I already talked about kinetic molecular theory. It's easier said than done to read about it than for me to explain it. So once you read about it, you have a little bit of a concept of what's going on before we go ahead and talk about the postulate. Now, kinetic molecular theory focuses more on gas. So we've done with states of matter. We've gone from heating curves to cooling curves. We've been able to calculate the heat between each section. But now we're really just going to focus on gas, right? Oops. Solid and liquid, not that important. We're going to focus on gas because scientists stated that our gas particles are actually meant to be acting in an ideal manner. However, realistically, they're not. So, if they were supposed to be acting in an ideal manner, we should be able to calculate certain certain aspects of the gas sample. So, we should be able to calculate the pressure, the volume, and the temperature based on its behavior of a based on its behavior. Give us 1 second. Okay, guys, sorry for that interruption. So, like I was saying, we use kinetic molecular theory to basically tell us how ideal gas particles should be acting. However, we then end up using the combined gas law because our realistic gas particles, do not act like ideal gas particles unless they're under certain conditions. So, we're going to learn about how our ideal gas particles should act. So, by reading, each paragraph gives you a little bit of postulate or an idea of how gas particles should react, and it gives you a couple of examples. So the first paragraph talks about gas consists of large numbers of particles that are far apart relative to their size. So even though we have large gas particles or small gas particles, our gas particles ideally should have a large distance between them. And it should all be equal depending on their size. We also then learn from the second paragraph that collisions between gas particles are elastic collisions, meaning that think of a rubber band ball, right? If you toss it up, it'll bounce off the wall, it'll bounce off the ceiling, it'll bounce off the doors, the chairs, whatever it comes in contact with. That is what they're saying gas particles should ideally react like, or move like. Gas particles are in a constant, rapid, random motion. They therefore possess kinetic energy. Yes, even though it is later found out that this is not actually consistent, we do ideally believe that gas particles are always in a constant, they're always moving, rapid, always fast, and random motion. Always not in a straight line motion, but always random. So this is how our gas particles behave. And then the last postulate, or the last idea that comes from the kinetic molecular theory, is that there are no forces of attraction or repulsion between gas particles, meaning that when you have two gas particles come together, they will neither be attracted or repelled by each other. They will just be. And we know based on chemical reactions that is just not true, and intermolecular forces, that's just not true. However, ideally, this is what we believe for gas particles as of right now. So, this is basically the kinetic molecular theory. So, like you know, what me and Mr. Short say in class, it's easier said than done. So let's go ahead and practice a couple of Regents problems on it. So, before we even get to the Regents problems, in which we will, right? So, before we get to the Regents problems, for our real gases to act like ideal gases, we must have low pressure and high temperature. Now, in chemistry, we like to call that plight. Pressure low, ideal gas, high temp. Plight. In the live session, we'll actually write it out for you and show you the setup of the way it's spelled. But we actually have on the periodic table and in nature and labs, two gas elements that act or behave like ideal gases. So they do act and behave like what the kinetic molecular theory says they behave like under these conditions. And those two gases are helium and hydrogen. So element 1 and element 2. Isn't that funny? So these two gases are the only gases found on the periodic table that under these conditions will act like an ideal gas. With that being said, go ahead, let's take a look at our Regents questions. So under which conditions of temperature and pressure does a real gas behave most like an ideal gas? Go ahead and answer that, and I will give you we will go over it and get the correct answer during the live session. And then question number 2, under the same conditions of temperature and pressure, which of the following gases would behave most like an ideal gas? Once again, answer this question, and we will review and get the correct answer during the live session. I'm going to give you guys a few minutes to go ahead and answer that before we move on. All right, so we're back. So another law we need to look into that also tells us how gas particles behave is Avogadro's law. Now, Avogadro's law basically says that gases at the same temperature, so Kelvin, at the same pressure, which could be kPa or atmosphere, and volume, which is liters, have the same number of molecules or particles. So as long as you have one of the same values of temperature, pressure, and volume as another gas, you will also have the same number of molecules. Now, what that means is if I have a helium gas at 25 degrees, 25 Kelvin, and it will have the same, and it contains a number of molecules. We don't know the number yet. It will also have the same amount of molecules if we had the same. Let me explain that again. I apologize. Explain that again. If we have helium at 3 liters, its molecules will also be equal to if we had hydrogen at 3 liters. Or if we had helium at 2 atmospheres, its molecules will also be equal to hydrogen at 2 atmospheres. So as long as they have one of the variables, either temperature, pressure, or volume, that are the same, they will have the same amount of molecules. I know I kind of confused myself there. I hope I didn't confuse you though. So let's go ahead and practice this Regents problems. At STP, which gaseous sample has the same number of molecules as 3 liters of N2? Now, anytime I tell my class, in my previous classes, to answer this, where does your mind automatically want to go to? What answer do you want to pick? And usually it's the same answer as the value you had in your answer choice. So if you said I would go ahead and choose 3.0 liters of H2 gas, you are correct. Always follow what your mind automatically wants to pick. So 2, at STP, which sample contains the same number of molecules as 3 liters of H2 gas? At this point, you should have gotten kind of a hang of it. So I'll let you figure that one out and let me know during the live session. Now, the last part of gas law, I know it says units of gas law, don't worry about it. The last part of gas law we need to figure out before we actually go on to gas law is we need to know that we're working with Kelvin, not Celsius. I do get in the habit of saying degrees Kelvin, but it's actually not degrees Kelvin, it's just Kelvin. So Kelvin is used because it has a larger range and allows us to get to absolute zero than Celsius. However, Celsius is the more common temperature measurement. So we need to be able to convert from Kelvin to degrees Celsius. When you were in earth science, you were able to convert between degrees Celsius, Kelvin, and Fahrenheit. We're just going to be focusing on Kelvin and degrees Celsius. If you didn't do this in the previous class, do not worry, it's pretty simple. Now, if you look right here, you'll notice that you have the temperature formula, which is K equals degrees Celsius plus 273. Now, K represents Kelvin, degrees Celsius obviously represents degrees Celsius, right? So all you have to really do is plug in the variable that you have and then solve for the variable you don't have. So for example, I have 25 degrees Celsius and I wanted to convert it to Kelvin. Well, this is my formula, right? And I'm going to just plug my 25 degrees Celsius where I have Celsius in the problem. And I'm going to do K equals 25 plus 273. And all I have to do is add them to find out what my Kelvin is. And my Kelvin would be 298. And that's how many Kelvins I would have. All right, now let's try to convert from Celsius to Kelvin. Let's actually try to convert from Kelvin to Celsius. So same formula, but now I'm going to plug in my Kelvin. So I have 300 equals Celsius plus 273. And because I want the Celsius by itself, I'm going to subtract 273 on both sides. And I should get my degrees Celsius